Welcome to Statistical Modeling at HEC Montréal. So in this video, we'll see the second covariance model for here longitudinal data only, and the omnious and very popular AR1 covariance model. Okay. So we seen the compound symmetry in the previous video, and this structure basically assumed that observations were interchangeable. And the correlation, conditional correlation, was the same for all measurements from the same individual. Okay. Of course, this seemed to fit significantly better than the model which assumed independent measurements. But and there was compelling evidence that this was doing much better in terms of adjustment. But it's not necessarily the best correlation model. Okay. There may be more adequate structure, and in fact, even though there's several choices, autoregressive models are sort of more natural for time series and longitudinal data. So let's have a look. Okay, so a sort of side note, here we're modeling the covariance, but it's actually not of particular interest. What we want to do is inference for the betas, right? I want to know what's the impact of vindictive complaining, word of mouth, how is revenge changing over time. But in order to do that, I need a sort of working correlation model that's good enough to capture features of data. It doesn't have to be perfect. Okay, it's certainly a model. It's a simplification of reality. And I'm not particularly interested in the parameters. Okay, other than the fact that I need these parameters to get valid inference for the beta. Okay, and I can again, if the models are nested, so we in a previous video we had a look at testing whether we could simplify it, whether the correlation between observations was necessary, assuming they were all equal and there was overwhelming evidence. So we can do model comparison using likelihood ratio tests if the models are nested. Otherwise, we can look at information criteria. Okay. So compound symmetry and AR1 are not nested. You cannot get from one to the other. So compound symmetry, basically two observations. They're interchangeable. They have the same correlation. Okay. So a simplistic model. But when we have measurements that are repeated over time, it's more plausible that the correlation decreases with the amount of time between observations. Okay. And basically, if you have two observations that are close by in time, they should be more correlated than two that are, say, 5 time step apart. Okay, so an AR1 structure is the simplest sort of model that can allow us to do that. And so this makes perhaps more sense on the correlation scale. So we'll have two parameters here, correlation rho and variance sigma square. Okay, so let me show you the correlation. Okay. So the correlation here, that's just basically we assume a geometric decay for the correlation. So correlation rho is going to be between -1 and 1. If you have positive correlation, which makes more sense, unless you have cyclical patterns, things go up and down. Okay, but typically rho will be positive. And so here, if you had, say, rho equals 0.5, well, we say the correlation between any two measurements that are 1 time step apart is 0.5. The correlation between two measurements that are 2 step apart would be 0.5 squared, a quarter. And then 3 steps apart, an eighth, and so on. Okay, and the covariance, that's just going to be, well, basically multiply every entry by sigma square. Okay, so we could have had a similar structure for the compound symmetry. So note you can't get from compound symmetry to AR model unless basically rho equals 1 or 0. Okay, rho equals 1 means that you just have perfectly repeated data, right? So that's more of a modeling problem. You're just so I would say desire for revenge, and this is constant, and I have just duplicated entries. So no good, perfect correlation. And the other scenario is in which they're actually independent. Okay, so it's both boundary cases. So they're not they're not one special case of another, and I cannot go from one to the next by setting restrictions on these parameters rho or tau, okay, unless rho and tau are equal to 0. So this is the AR1 model. I'm saying that this sequence is decreasing, so correlation decreases and at an exponential rate. So same structure really to fit the AR1 model. Here I'm actually going to need to specify the time ordering because that matters. So specify tcat, okay, this copy of time as a categorical variable, and also the ID. And there I say, okay, well, the time measurements, that's tcat, subject are grouped by ID. Okay, so each individual, that's a particular ID, and I'm specifying an AR1 correlation. Okay, so now you can see in the estimated covariance or correlation, so here I almost have 50% correlation, which is much higher than I had for the compound symmetry. There I had something like 35%, and that's due to the fact that the compound symmetry is a sort of average between the two. Okay, so it's averaging all the entries. So here I had, okay, 0.5, 0.25, 1/8 is 0.12, more or less, and so on. And you can see that the estimated variance is 0.37, so that hasn't really changed. So rho 0.49, sigma squared 0.377. You have these in the entry, so AR1, that's a correlation parameter. And you can really check that the formula for computing the covariance matrix is actually what's given up to running in the slides. Okay. So mean parameters here, they're slightly different, but very similar to the compound symmetry model. And again, you'll see, so here sex, for example, the p-values change a bit, but it's still not significant. Okay. So there seems to be still an effect of age, victim complaining word of mouth. And you can also see that degrees of freedom have been adjusted accordingly. Right? So sex, we rarely have 80 measurements of sex and not 400. And so this is not 400 minus 6. It's so only for time is adjusted accordingly. Okay, so there's some formulas. Of course, 75 degrees of freedom is basically a normal distribution for a student. Okay.